Section 2 in rotational motion is called the rotation of a rigid body. So now we have some shape, some object that cannot be simplified to just a simple point, a particle. So we're going to have to do something called dealing with an extended object. So in this case, we're going to have to deal with something as we're dealing with the extended object, and we're going to consider that a rigid body. So that's where the size and shape of the object does not change as it moves. And this is, again, an object that we cannot simplify to just a simple particle. For example, wheels on an axle. Um, as it moves, it can be doing one of three things as this rigid body is moving through space, right? So not like outer space, but through some space. So it could be translating without rotation. So like if I hold a stapler or like a pencil or something, it's just pushing through the medium that it's in, but it's not turning in any way. It's not rotating. It's not spinning. It's just kind of moving through. Okay, so like that. Rotational motion would be where the object is not translating, but it is turning. So it's rotating about a fixed point, and that fixed point is within the body itself. So within the body itself, and the object is turning about that fixed point. Okay. So that's called rotational motion. And then we also have a trajectory. So that is a combination of translational motion and rotational motion. And so we have combination motion where the object is in some sort of trajectory. So that could be that the particle is in like a projectile motion, but as it is in the projectile motion, the rigid body, so the extended object, is also turning. So as we see in the picture here, the object has changed its orientation as it is flying through the air. So that trajectory motion, that combination of projectile and rotational motion, makes a very complicated path, and that's not something we're going to study right now. Translational motion really is fairly boring for rotational motion studies, so we're not going to do that right now. That really is more like what we did before. So we're focusing on rotational motion right now, where the rigid body is spinning about itself, and the object itself is not moving. It's just turning about a fixed point within itself. So the figure here is showing a rotating axle for some time interval delta t. The 2 points 1 and 2. So we have point 1 here and point 2 here on the wheel are moving different distances because they are one is closer to the axis of rotation than point 2 is. So the axle here is acting as our axis of rotation, okay? So since point 1 is closer, it has less distance to turn than point 2 does as we rotate about that axis of rotation. All right, so now if I'm looking at it from this direction, the axle is rotating in this counterclockwise direction if I'm looking at it from that direction, right? So point 1 is rotating counterclockwise. Point 2 is also rotating counterclockwise, but because point 2 is farther away from the center of rotation, that axis of rotation, point 2 has actually traveled farther, okay? So delta theta 1 would be greater than delta theta 2, although the entire wheel is turning at the same omega. The angular velocity is the same for the entire wheel. Point 1 is turning faster than point 2, okay? Because they have to be in order for the entire wheel to stay together. Hopefully that makes sense. So the angular velocity, omega, is the same for every point on the rotating rigid body. Okay, so with that in mind, we can go on. In uniform circular motion, the object is rotating at a constant speed. Remember, some sort of uniform motion means some sort of constant thing is going on. So in uniform circular motion, we are rotating at a constant speed. So if we have non-uniform circular motion, then the speed is somehow changing, okay? And if something is changing, if the speed is changing, then that must mean there is an acceleration. So in this case, if the speed is changing in our rotational motion, then that means we must have an angular acceleration. There is an acceleration that is speeding up the speed of the rotation, okay? So now we're finally going to learn this time about angular acceleration. So in the wheel here in the picture, the angular velocity is changing, all right? As we can see, we started off here. The dots are very close together, and then they're getting farther and farther and farther and farther and farther apart. So that means the wheel is speeding up. So we have an omega initial, the initial angular velocity, and an omega final, the final angular velocity, which means we must be able to calculate an angular acceleration. So we have an initial time and a final time for our initial angular velocity and our final angular velocity. So we would be able to calculate delta t, and we'd be able to calculate a delta omega. So therefore, based on what you learned from linear equations, we should be able to deduce pretty easily what our equation for angular acceleration will be, and that's going to be on the next slide. So recall that we defined linear acceleration as a sub x, if it was in the x direction, to be delta v sub x, so the change in velocity over change in time, and that was v sub x final minus v sub x initial over delta t. So as we saw in the last section, there is a definite correlation between linear and angular stuff, right? So now, what is our angular acceleration going to be? Well, this symbol right here is our symbol for angular acceleration, and that is the Greek letter alpha. It is not an A. It is like the fish symbol, okay? So that is the Greek letter alpha. And remember that we have the Greek letter omega for angular velocity, and that is a more loopy looking W, but it's not a W. It's the Greek letter omega. So we have the Greek letter alpha for angular acceleration, and we have the Greek letter omega for angular velocity, and we have the Greek letter theta for angular displacement. Okay, so we have alpha is the change in angular velocity over the change in time. In other words, delta omega over delta t. So that's the angular acceleration for a particle in non-uniform, that's very important, circular motion. Because if it's a uniform circular motion, then the angular velocity is not changing, which means the angular acceleration would be zero. There would still be centripetal acceleration, but no angular acceleration, okay? The units of angular acceleration are radians per second. In other words, radians per second squared. So positive and negative values of alpha, angular acceleration, can't be interpreted as simply speeding up or slowing down. So this is like when we were dealing with linear acceleration, because we need to know what direction the thing is going, which means in this case with angular, we need to know what direction the thing is turning. So like omega, alpha is the same for every point on a rotating rigid body. So alpha for this point will be the same for alpha for this point and so on, okay? Because the wheel has to stay together. The sign for alpha depends on the direction of rotation and whether the object's rotation is speeding up or slowing down. So alpha is positive when the rigid body is, so in this case, alpha is positive when the rigid body is, notice that omega is this way, okay? So we're rotating counterclockwise and speeding up. We have a positive alpha in this case. Now notice this time omega is clockwise, but the dots are getting closer together, which means that we are slowing down, okay? So rotating clockwise, slowing down. This means alpha is going this way, okay? That means alpha is positive. So the alpha would oppose the motion in this case, which means alpha is going counterclockwise. In the case on the left, omega was counterclockwise. We're speeding up, which means alpha must be in the same direction, which is why alpha must be also positive, counterclockwise. okay? They have to be in the same direction for us to be speeding up. They have to be in opposite directions. They being omega and alpha have to be in opposite directions in order for us to slow down. So let's take a look at the ones on the right. Alpha is negative when the rigid body is, but more importantly, think about the concept. Notice that omega is counterclockwise. So we have omega is counterclockwise. Now, what is the object doing? Well, as we rotate around counterclockwise, the object is slowing down, which means that alpha must oppose the motion. So this is alpha. Now that means that the object's acceleration is counterclockwise? No, it is clockwise, which means that alpha is opposing, it is clockwise, and that makes it negative. Okay? Because positive is counterclockwise. Okay, this time we have omega pointing this way. We are rotating clockwise. So this is our omega. All right. Now, watch the dots. We're rotating clockwise. So we start here, and the dots are getting farther apart. In order for the dots to get farther apart, meaning we are speeding up, alpha must be in the same direction. So alpha is this way. Okay, so that they are both going the same direction. So this is our alpha. In that direction is clockwise, and clockwise is negative. Therefore, alpha is negative. So that's how you figure those out, okay? You got to see which direction omega is going. Are we speeding up or are we slowing down? And then based on that, is alpha positive or negative? Do we have alpha going in the same direction or in the opposite direction? Okay. So the important note is don't confuse angular acceleration with centripetal acceleration. There is always centripetal acceleration toward the center of the circle. Angular acceleration just tells you how rapidly the angular velocity is changing. If we don't have angular velocity changing, then we don't have angular acceleration. Centripetal acceleration is a vector quantity that always points toward the center of the circle. It's never zero if we have circular motion, okay? So remember, circular motion is analogous to linear motion. So instead of position, we have angle. Instead of velocity, we have angular velocity. Instead of acceleration, we have angular acceleration, okay? And those all correlate between the variables that we used to use. So this chart kind of illustrates that. Position was meters and used the variable x. In circular motion, x becomes theta. And we talk about the angle, and the units there are radians, okay? For velocity, we had meters per second, and we calculated that using v sub x equals delta x over delta t. The correlation there with circular motion is velocity turns into angular velocity. We calculate that with delta theta over delta t instead. And the units there are radians per second, not meters per second. With acceleration in linear motion, we had a sub x equals delta v sub x over delta t. In circular motion, we have angular acceleration, which is delta omega over delta t. The units are radians per second squared, not meters per second squared. Our equations for constant velocity, delta x equals v over delta t. Well, for constant angular velocity, we have delta theta equals omega delta t. Okay, the direct correlation there, you can see how the variables switch over. We have delta v equals acceleration a delta t. For constant angular, we have delta omega equals alpha delta t. Okay, it's the same, we just swap the variables. Constant acceleration equation, again, we have delta x equals v delta t plus 1/2 a delta t squared. Swap the variables over, and now we have delta theta equals omega initial delta t plus 1/2 alpha delta t squared. It's the same equation, we just swap the variables. All right. So when we're graphing, the angular velocity is the slope of the angular position versus time graph, and the angular acceleration is the slope of the angular velocity versus time graph. Exactly what we learned first semester when we were dealing with the slope of the position versus time graph and the slope of the velocity versus time graph. All right, so enough of that. Let's try some problems. A disk in a computer disk drive spins up from rest to a final angular speed. So this would be before solid state drives. We're talking about a hard drive. Final angular speed of 5,400 RPM in 2 seconds flat. What is the angular acceleration of the disk? And at the end of the 2 seconds, how many revolutions has the disk made? Okay, so the first thing we need to do is realize spins up from rest. That is an omega initial of 0 radians per second. Okay, and then 5,400 RPM, revolutions per minute. Remember, revolutions is not really a unit. So revolutions per minute is a frequency that they gave us. We have an omega final that we can turn into a velocity, angular velocity, using the 5,400 RPM revolutions per minute. Okay, so we'll turn that into radians per second, an actual velocity, by converting this to, let's get rid of minutes and turn it into seconds. There are 60 seconds in 1 minute. Revolutions doesn't really matter. And I can say, let's do this. I can say there are 2 pi radians in 1 revolution. Okay, so now the revolutions are legitimately gone. The minutes are gone, and I'm left with radians on top and seconds on the bottom, which is what I wanted. And when I multiply this out, I wind up with significant figures gives me 565 radians per second. Okay, so it's pretty fast. Now, once I have that, the question is, what is the angular acceleration? So I have alpha is angular acceleration, is delta omega over delta t. Well, the change in angular velocity was 565 minus 0 radians per second, so it's just 565 radians per second. Over delta t, they told me was 2 seconds. And I'll get my answer of 283 radians per second squared. Radians per second per second. Okay? And then they said, how many revolutions has the disk made? So revolutions has the disk made means delta theta. So I need a delta theta equation. And that will be this one, omega initial delta t plus 1/2 alpha delta t squared. I know alpha and I know delta t. Also, I know that omega initial is 0. So that term is gone. And I have just the last term. So I have 1/2 times my calculator's answer, not this one, times delta t, which was 2.00 seconds squared. So really I have 4 times 1/2, which is 2, times my calculator's answer of 283. And I wind up with, after significant figures, 565 radians. So how many revolutions is that? Because it asks for revolutions. So how many radians are there in a revolution? Well, there are 2 pi radians in a revolution. So we go ahead and divide by 2 pi, and we wind up with 90-ish revolutions. And then we're done. So it takes 90 revolutions for it to spin up to 5,400 revolutions per minute, and it takes 2 seconds to do that. All right. Now, the figure here shows the angular velocity versus time graph for the propeller of a ship. So describe the motion of the propeller. Draw the angular acceleration graph for the propeller. Okay, so first, describe the motion of the propeller. So we see a couple things happening here. I see this region right here, and I also see this region right here, and I see this region right here. So the question is, what's going on, right? So what's going on? So I see a negative angular velocity in this region right here. Then I see a positive angular velocity in this region right here. And then I see a constant angular velocity in this region right here. So what's happening? The motion of the propeller. So it seems like it was turning a negative angular velocity, means it was turning clockwise, but slowing down, right? Because it's getting closer to zero here. It was actually stopped right there briefly. Okay, now here, what's it doing? Well, it has a positive angular velocity. So in this region, it is turning counterclockwise. And because the numbers are getting farther away from zero, it is speeding up. Now, finally, what's happening here? That's a constant angular velocity. So it's holding steady at 8, looks like, radians per second. Okay, so now part B, just draw the angular acceleration graph for the propeller. Okay, so this would be time in seconds, and then angular acceleration is here, and that would be radians per second, or radians per second squared. Well, that is the slope of the omega, right? The slope of the angular velocity. So we just gotta figure out what the slope is. And if I do that, let's see, we are up here at 8, and it's 8, and we're down here at 0. So we have 8 minus the y coordinate of 0 over, and then the x coordinate is, let's see, 4. Oh, no, it's 8 minus 4. Okay, so this is 8 over 4. Seems like the slope is 2. Okay, so that means that the angular acceleration this entire time, since it was linear, was 2. So I can mark 2 right here. And from 0 to here, which is 8, I have a horizontal line of 2. Then in this region right here, that is a constant slope as well of 0. So we're going to drop down to 0, and we're going to be 0 the rest of the way. Okay, that's how that works. All right, now we have uniform circular motion in the little graph on the left and non-uniform circular motion on the right. So on the left, we have uniform circular motion. That means the velocity here and here and here is going to be the constant the whole time. We have centripetal acceleration here and here and here, always pointed towards the center of the circle, and it's going to be constant the entire time in magnitude, but not in direction. Okay? Now, for non-uniform circular motion, we have the tangential acceleration now as well as the centripetal acceleration. So centripetal acceleration is still there, okay? But because the particle is speeding up or slowing down, the centripetal acceleration magnitude is actually also changing because the force required to keep the particle moving around in the same circle is either going to grow or shrink depending on the velocity of the particle or the rigid body, depending on what it is, okay? So if the velocity is increasing, then we have this tangential acceleration here that is causing us to speed up. That tangential acceleration could be positive, could be negative, could be growing, could be shrinking. We don't know. It just depends on, is the velocity getting bigger or is the velocity getting smaller at a constant rate or a non-constant rate, okay? So tangential acceleration causes the particle speed to change. There is a tangential acceleration only when the particle's speeding up or slowing down. There is always centripetal acceleration. That causes the particle's direction to change. As the particle speeds up, the centripetal acceleration gets larger. Circular motion always has centripetal acceleration. We got to remember those two things are distinctly different from each other. So recall that the magnitude of the centripetal acceleration is this equation here. Okay, we have that. Tangential acceleration is what we have just learned. These guys here. And now we have this extra one, alpha times the radius. Okay, so now we have a bunch of formulas for two different types of accelerations that we're going to have to use. And the last thing for this section now, a ball on the end of a string swings in a horizontal circle once every second. State whether the magnitude of each of the following quantities is zero, constant but not zero, or changing. So each one of these requires an answer, and they could be all the same, could be different, we don't know, okay? But it's not like we're choosing one answer. Each one requires an answer. So take a second to think, and we'll come back. So the ball is on the end of the string, and it's swinging in a horizontal circle once every second. This means, so horizontal circle once every second, that means that the angular velocity, omega, is constant. That also means probably that alpha is zero. Okay, so now that we have omega is constant and alpha is zero, we have these choices: zero, constant but not zero, changing. Okay, so the velocity. The velocity is just like the straight line velocity, right? So velocity for A, what is it? The velocity of the ball as it moves would be constant but not zero. Definitely not zero. You could argue changing because of the velocity being a vector, and as this thing spins around, it would be changing. And I would actually, let me agree with you on that one. Changing, but I think the intent is the magnitude, right? So we're talking about the magnitude. The magnitude would be constant. It's definitely not zero. The vector is changing, but the magnitude is not. So it's constant, but not zero. Now, B, the angular velocity would be constant, but not zero. Okay, angular velocity, constant, but not zero. And that's because the angular acceleration is zero. Angular velocity is that guy. Okay, so it's not zero. The thing is moving around a circle. Centripetal acceleration. We always have a centripetal acceleration. If this thing is going around in a circle, then there is a centripetal acceleration. It is not zero. This does not have an acceleration tangentially, so therefore it is constant, but not zero. Okay, D, angular acceleration. Well, we already said angular acceleration is zero. And tangential acceleration. Again, tangential acceleration is this guy, zero. So that's how you do that one. All right, that is the end of the section.